Hi, everyone. I'm Marcello Galhardo. I work in the AndroidX architecture components team at Google. And today, I'll be talking about the commonization of the lifecycle libraries. Before I start, to set the expectations, the talk is designed for app developers that would like to migrate their libraries from Java or Kotlin to Kotlin Multiplatform. If you're an app developer, you can still get some insights of how we took some of the decisions around the lifecycle libraries, but the talk itself is not designed for you to use the lifecycle libraries in your app. So first, the agenda for today. We're going to be discussing about the Android support for Kotlin Multiplatform, announced in Google I/O 2024. We will discuss the timeline to get lifecycle KMP stable released. And then we're going to talk about the API challenge that's going to be most of the content. It's going to be mostly code. So if you have been doing Android for a while, you might know that we introduced the architecture components library in 2017. At that time, we had the Java first ecosystem. We were doing UI with Vue and XMLs and so on, the traditional one. And fast forward to 2024, the scenario is very different. Now we have Kotlin first, and we also have the modern UI toolkit Compose. We also announced the Kotlin Multiplatform support officially. And first, we need to discuss what does it mean to have Kotlin Multiplatform support in the AndroidX libraries. Basically, there are two types of support level, kind of. So there is the KMP compatibility and KMP support. KMP compatibility are libraries that can be used in your common source set, but you might need to write the integration yourself. An example of these libraries are Lifecycle. If you're using Lifecycle in a KMP project, you might have to write your own Lifecycle owner, or using something like Navigation Compose provided by JetBrains, the KMP fork. There is also KMP support, which is like the dream word, and here is exactly as before, but everything works out of the box. You can just include the dependence, and things just work. An example of that is Room, if you're using the artifact with the SQL driver, where things just work. There is still a bit of learning here on which library should get each type of support level. We are still learning about that, and yeah, there is no clear answer at the moment, but overall, there are this distinction between the libraries. For the timeline to the lifecycle KMP libraries, the main goal was to get the Navigation Compose Multiplatform released, and the project ran in 2024 from January to May, and we did partner with JetBrains. Basically, they really want to get a navigation library for Kotlin Multiplatform, and we were really happy that they also want to collaborate with us in that. So JetBrains was focused on get the navigation KMP release alpha, and I think it was released Kotlin Conf. And we were mostly focused on how to unblock them as much as possible. So our work was to understand what they needed to get that done and try to get things out of the way. That means, in this case, take the navigation dependents and make them multi-platform. These dependencies are such like lifecycle common, runtime, and view model. So now it's going to be most of the talk. And we're going to discuss briefly about the lifecycle in itself, and there will be a lot about view model, because view model had more difficulties to migrate compared to lifecycle. Lifecycle is quite a simple, high-level API. First, lifecycle event per platform. If you have been doing Android for a while, you are probably familiar with the lifecycle events, such as on the start, on the resume, and so on. On iOS, we do have callbacks that kind of translate quite well to the lifecycle events that we had. So if you had something like did become active, that can be translated to on resume, or will resign active can be translated to on pause. For desktop, that is also true. You can basically take these callbacks and translate them to specific multi-platform lifecycle events. For web, for the root lifecycle owner for the web is a bit more limited. Basically, we skip all the way from create, start, resume, and there is focus, and we go to on pause, on blur, and if you close the tab, your application is basically destroyed. So, view model provider. If you use the view model libraries using the high-level APIs that we provide, such as the view models delegate or view model composable function, basically that's more or less how we're going to do it. You have the delegate that takes in a factory and returns the view model. In compose, you have the view model composable function that you can just create and initialize a new instance. Behind the scenes, both of them are using the view model provider and calling the get from it with some flavor on it. So if you did use view model with Java code apps, you probably know about view model provider and so on. If you just start with Kotlin, you might just know about the extension function that I hope everyone is using. Basically, we're going to be talking about the view model provider, which is the main API surface. The view model provider is a simple class that exposes most of the APIs that view model needs. We're not going to expose all the methods from the view model provider. We're going to just talk about the ones that had some kind of challenge when they were migrating. So it's just a subset, and it's purposely simplified for the doc. First is the constructor. The view model constructor basically takes in a view model store, a factory, and a creation extra. The view model store is the entity that's going to hold the instance of view models. When there is a configuration change, it's going to be retained in memory, and when you recreate the view model provider with the old store, it's going to be used to retrieve the view models. The factory knows how to create view models, as the name suggests. And the extras are a way for you to customize the view model creation when the factory is called. The get function is the one that orchestrates all of that. Basically, the get function will check against the view model store. Hey, there is a view model created already. If there is, it returns. If it doesn't, call the factory, creates a new instance, put in the view model store, returns it. The factory creates view model instance, taking the string and a class. Actually, a class and a creation extra, and returns the view model. There are two default implementations of the factory, the new instance factory, which is the one that is used when you create a view model with no args constructor. And there is the Android view model factory that is very similar, is a specialization, and also takes into account the Android app application if you have a one-parameter constructor. The companion object basically has some utilities that we can use around integrating with the view model provider. So for the constructor, as you can see, assuming that all of these parameters are Kotlin Multiplatform compatible already, you might assume that you can just take this constructor and move it to Kotlin Multiplatform. If you look closely, you will see that there is a default constructor, default parameter in the creation extra, and is annotated with JVM overload for Java interoperability. So let's say we take this view model provider constructor and move it from Android main to common main. And theoretically, everything should work. If we build the project, it's going to work. And something we have in the AndroidX repo is basically we have some tooling for check against the public API of our libraries. We use MetaLava, but there is also the one provided by JetBrains, Kotlin binary compatibility validator. And by calling Gradle check API against the AndroidX repo, you're going to check what changed in the public API of that constructor. So by moving the file without changing anything and everything compiling, if you run the check API, there was a change in the public API. If you look closely, the constructor was removed, and the new constructor was added with the same number of parameters. It seems that this optional keyword, for some reason, is not identified anymore and disappeared from the code when there was a move. So what is this optional keyword? What we can do to understand what is this is we can take the code before and after the compile and check the Java bytecode to see what changed. Basically, we do get these three functions when we use the JVM overload in a constructor with a default parameter. The first two is what we expect from the Java point of view. We get the two constructors. One doesn't have the creation extra. The other one has the ability to pass one, and that's it. However, there is a third one. The third one is a syntactic method that is public and takes in an additional last parameter called default constructor marker. And this is not available on, like if you annotate a constructor with JVM overloads on common main, that constructor is not generated anymore. And there is a public issue open about that. And basically, that constructor seems to be used for some Kotlin compiler optimizations. And if we touch that constructor and move it or remove it, et cetera, that would be a binary incompatible change because that is a public syntactic method that could be being used by other libraries that is compiled against an old version of view model. So what can we do here is basically, we can go back to our constructor. We can introduce a new create method that is only available in the common source that calls the view model provider constructor on Android, and basically does nothing else more, just for backward compatibility. So the constructor is now Android only, and there is a new create method that you're expected to use if you're using the view model provider manually on your common source set. And that's the main reason that we had to introduce this new create method. So the learning here is basically, if you are moving files between source sets, things might break without you know, and you should have some kind of way to check your public API. In our case, we have MetaLava. Again, there is also Kotlin binary compatibility validator, but just have something in place to detect that in your CI or, yeah. So for the get function, the get function takes a key string, a model class, which is a class, and that's it. It's quite simple, but if we expand the types, we're going to see that there is a java.lang.class. Java.lang, as the name suggests, is a Java type. It's not available on Kotlin Multiplatform. So what we can do here to fix that is we can duplicate the method, create a variant with key class that calls the previous one. And this would keep backward compatibility, compiles, and everything works. And we get an error report because someone was mocking the view model provider get, and now because class and key class are like same number of parameters, it seems that their mock library didn't manage to detect which one is each. There is an ambiguity problem, and it doesn't compile. So the learning here is don't use mocks. And definitely don't do that with the view model provider.get. Yeah, factory. It's similar problem. Takes a class, java.lang.class. As you can see here, we're going to do a similar approach. We're going to duplicate the method. There is now two, one that takes the key class, and we're going to call one from each other. The unsupported operation exception is actually the default implementation, just for you to know. And basically here the learning is if you do have Java types in your public API, they will be a bit challenging to change if there is no one-to-one with them, and you might need to duplicate your APIs or find some workaround to fix that. Okay, the new instance factory. The new instance factory, if we expand the content of the new instance factory, which is again the factory used to create view models with no args constructor, you're going to see that it's called model class.getDeclared constructor, not new instance. This getDeclared constructor and new instance is basically reflection. We take the constructor and invoking it. And, well, this is not available for all platforms exactly. We can include a Kotlin.reflect.full, which is the artifact that JetBrains provide with more functionality for our platform. But this is a very large dependence for a library like view model and lifecycle. And we would be adding that for one method call. So, yeah, the learning here is mostly not all APIs of your library might be worth to migrate to Kotlin Multiplatform. So sometimes it's okay to just something that is quite easy to do in a specific platform might not compensate in all platforms, like the creation with reflection. Plus, most people are going to be writing their own custom constructor if they're using DI and so on. So the Android view model factory is a specialization of the new instance factor, so we know that we're not going to convert that because new instance factor. And if we expand the content, it takes in an Android.app application, which is very Android specific. Here, yeah, basically, not everything has to be commonized. It's not because you're moving a library from Java or Kotlin to Kotlin Multiplatform that you literally need to make all the public API available in common. Some APIs might not make that much sense to commonize, especially something called Android view model factory. So if you do KMP, you might be familiar with this expect class. Basically, you can annotate a class with expect. This will be available in the common source, and then each platform can, when necessary, can implement a different variant of this class. Here we're going to be doing the view model provider expect to actualization. We're not going to convert everything, as we said. Some methods are only available for Android or JVM and so on. New instance factory is JVM, Android view model factory, and the constructor is Android, yeah. And then we have the get, factory, and the companion object that we want to migrate. Oh, I pressed the button. Basically, like what we would expect here is the get function is basically something that is exactly the same in all platforms. So we could just write a default implementation for that, and we share that in all platforms. And then the specific parts of each platform, we can just do it in that platform. That's what normally we would expect. So expect declarations don't support default implementations at the moment. So you cannot actually write a default implementation in the common source set. You need to handle that yourself. If we filter the number of files in the AndroidX repo of view model provider implementations right now, we basically have 3 variants, the Android, desktop, and non-JVM. And we don't want to duplicate that 3 times. So what can we do here instead? Basically, we can extract the logic from the view model provider, and we can make this new object that holds the logic, multi-platform, and each platform will just access this object. Basically, each platform is going to have an opaque class definition that's calling the other object. We can do that by, in our case, we call it the view model provider implement. And this is an internal view model provider class inside the view model library. And we just create in the constructor a view model provider implementation that holds all the state, behavior, and logic. And then whenever you call a method in the view model provider, we pass the callback to that specific platform. The view model provider implementation is exactly the same as before. So most of the logic here can be just migrate to Kotlin multi-platform. But if you remember the factory that we introduced a new key class parameter, this factory only have the key class available in common. The Java is not available anymore. So we had to change the parameter here because it's common source to key class. And then now we modify a bit the code to just call factor.create.model class, model extra, looks right, and OK. And by doing that, we revert a 2-year-old fix related to the sugar and compile own dependence in library projects. Specifically, if you use a leak canary with 2.80 or 1, you might get an exception that the abstracted method error has been thrown and so on. This is already fixed, but yeah. So how can we fix it? Factory.create, we can introduce another definition of expected function. Instead of class, now is a function, passing all the parameters. And then this expect function in almost all platforms is exactly the same. Just call factor.create, model class extra, and we're happy. And on Android, we actually need to backport that. So because we are on the Android platform now, we can actually call each variant that takes different versions, like Java version or Kotlin or so on. So what we do is basically, we try to call the key class with the extra. If that works, great. If that doesn't work, it's going to throw an abstract method error. We're going to catch that, and we're going to try again with the Java variant. If that doesn't work, we try again without the default creation extra for backward compatibility. And well, what we did here is basically, we have the view model provider for desktop, Android, and non-JVM, which are duplicated files for each platform. And then we have the view model provider implementation, which is shared between all platforms with Kotlin multi-platform. And then we have, again, a create view model method that is expected for each platform, which is basically the same in all platforms except Android. And just to re-inject the previous code for backward compatibility. So the learnings here is, first, you cannot have expect class with default implementations, so you need to handle that yourself to avoid duplication. Second, if you have clients use the sugar modification that can cause side effects, and that's actually quite tricky to detect. We did write tests and stuff for detecting that one, but it's very difficult to understand like where things are going to explode because of this. And the third one is you can mix and match expecting the actual to reuse common code. And although this is great for reusability, this also means that you need to test your code for each one of those new platforms. So in this case, we're going to need to write specific tests that cover the Android desktop and JVM and the combinations of them and so on. So the view model class. Again, if you have been doing Android for a while, you pretty much familiar with what's the view model. You probably extend this class to write your view model. We're not going to talk about the most common methods because they're quite simple. Constructor, onCleared, cleared, and so on. What we're interested here is the add closable API. Basically, the add and get closable API allow you to bind the resource with the lifetime of a view model. So if you have some kind of expensive object that you want to clear, close, clean, something like that, connected to the view model itself, you can add it using the add closable, bind the key with that, and whenever the view model is cleared, these closable are going to receive a call on the close and it's going to be closed. You can use the version without a key, or if you pass a key, you can retrieve that with the get closable. We are also going to talk about the view model scope and how we handle the coroutine scope creation on each platform. So for add closable, if you expand the types, you're going to see that that's java.io.closable. And java.io.closable is not actually ported to Kotlin Multiplatform. We do have the auto-closable, which java.io closable extends. So we can change that to auto-closable. Basically, we can change the method signature to auto-closable. We are very lucky here because the variants with the key are not stable yet, so we have the ability to actually, okay, let's just update, and that's fine. However, add closable was a stable API at the time. So we do need to maintain binary compatibility. So we have to we have to keep this add closable that takes the java.io.closable only on Android platforms, set was hidden, to allow libraries that were compiled against the old version to still compile exactly equal. And because of that, now we also, again, have to have multiple variants of this view model per platform, because that is Android specific. So again, filtering the view model that we have. We have the JVM, non-JVM, so a bit better. And we're going to do the same thing. Now we're going to have a view model implementation, and we're going to just be calling the methods again. And this view model is basically an empty class that doesn't do anything else except by calling the view model implementation. The view model implementation, most of the implementation is like the same. It's easily converted to Kotlin Multiplatform, except by synchronization. Synchronization is not stable in Kotlin Multiplatform. Actually, for you to use synchronization in Kotlin Multiplatform, you do have to use the atomic foo library. And atomic foo, well, if we check the release notes, the README file, sorry, you're going to see that it's quite experimental. Like the lock support inside atomic foo is experimental within the library that is experimental, and there is no guarantee whatsoever of compatibility. So we cannot just throw that inside the AndroidX library. So how can we do that is we can write our own synchronization logic. So basically, we're going to introduce an expect class, synchronized object. We're going to have a synchronized method and a synchronized implementation. You might find it interesting that, or weird, that there is a synchronized method that's final, but there is a expect inline synchronized implementation that is called from the final variant. So why that? Well, we do want to use a contract to give more information for the compiler when this synchronized method is called. And contracts are not supported when you use in the expect declarations, so we need to work around that. So for JVM environments, that's quite easy. We can just call the Kotlin.synchronized. The API contract is pretty much the same, so you can just need to pass them the parameters from one to another, and that's cool. For native platforms, we're going to need to implement the synchronized object. And basically here we have the synchronized object with a lock and lock. We lock the object, we call the action that is passed, and then we unlock that. For the synchronized object, we are not going to cover the whole implementation of it, just the interesting aspects of. So if we expand the synchronized object, the point I want to call attention here is this experimental foreigner API. Basically, you're going to need to use POSIX in different platforms to control the lock and release and so on. And yeah. Basically, the learning, why I'm showing that is basically that it's really cool that Kotlin Multiplatform allows you to use native APIs on a specific platform, but it's also, you will need sometimes to touch these APIs and learn about them and how to use them. So keep that in mind. At least until atomic foo gets stable, I guess. So another interesting here is that there is a random integer that is expected. And basically, this flag is actually different depending on the platform. Sometimes it's signed, sometimes it's unsigned. So we actually need to handle that as well. That is quite easy, but a bit weird. On Daring, you can just return the integer. On Linux, you can convert it to integer. But there are some small things like that that you have to do sometimes. It is a bit weird if you're just browsing the code and having a look and seeing these random things happening, like why they did that. Well, right, the view model scope. The view model scope used the APIs we built before, so it used the synchronized that we made ourselves. It used the get closable, add closable with the key, and yeah. The most interesting aspect here is the closable coroutine scope, which implements the out closable and coroutine scope. And whenever the view model is released, we call the coroutine context.cancel. And there is a dispatcher main here, which is also not available on all platforms. So we will need to handle the dispatcher main ourselves. Basically, we can introduce a create view model scope. And different from before, the create view model scope will not going to be an expected function. We're going to just handle the exceptions ourselves. If you do have the dispatcher main available, we just return it, and we are happy. If it's not available, we're going to get a not implemented error. That's going to happen in native environments, specifically Linux. And then we're going to fall back to the empty coroutine context that's going to be used was the default one. If you are running JVM desktop with Swing, you're going to get an illegal state exception. So we're also going to fall back different exceptions, yeah? And they're going to fall back to empty coroutine context. Finally, we're just going to return the same object. The dispatch is going to be concatenated with the supervised job, and that's it. Yeah, so the learning here is not everything has to use expected actual declarations. They are a really cool feature and very useful, but sometimes it's easier to just handle the exceptions. And if some different exception happen, in this case, for example, it's going to crash, and we're going to be able to detect that there was something unexpected. So the 3 key takeaways from the Android point of view, AndroidX point of view, working these libraries, or me, is the first one is finding the balance between minimal change against the best common API might be quite tricky. You do want to provide a really good Kotlin multi-platform experience, and at the same time, you don't want to start to modify everything and forcing all your current clients to change their calls, APIs, and break compatibility. And it's very interesting here to also try to maintain consistency. So if you have a class that take a Java.lang class, you can just make a Kotlin.k class. Also, you do want to reuse your knowledge. So if you are building a library like with many customers and clients, you don't want to just reinvent the wheel and start to do everything again, new abstraction implementations, and have to maintain 3 different ways of doing things. You want to keep consistency, and you want to reuse what they already know to build on top of that. And finally, Kotlin multi-platform is quite powerful. It's true that there was a lot of gotchas and weird things, but at the same time, this is a library that was developed in 2017, so I guess this is 7 years from now. And we did all the way from Java to Kotlin multi-platform without breaking backward compatibility. And this shows how flexible Kotlin in itself is. Yeah, that's all I have. Thank you.